So in this video, we're going to talk a little bit about acids and bases. You know some of this from previous chemistry courses, from Chemistry 110, if you took Chemistry 110 at Lyco. And we're just going to talk a little bit about what it means to be an acid, what it means to be a base. So when we start off, the idea of acid and base that we're thinking of, or that we're referring to or talking about in this particular part of the course, we're talking about what's called a Bronsted acid, where a Bronsted acid is a molecule that will donate or give up a proton. Proton is an H plus ion. Remember, hydrogen has one proton and one electron, and so if it's plus one, it's literally just a proton. So what we're doing is, or what that acid is doing, is donating that proton. Now, a general form of an acid, which isn't really technically chemically correct, but it's a shorthand that's used very often, is HA, where H is the proton that particular acid will donate. A is the anion that is left over whenever it donates that proton. And in this case, it's donating that proton to water. That water becomes what we're going to call the hydronium ion, or H3O+, and we're left with the anion from that particular acid left over. So the acid donates that proton. Now, we're going to talk about different classes or different types of acids, the first of which is going to be the strong acid. And a strong acid is going to donate all of the protons that it has available to donate. So for instance, hydrochloric acid, it's going to donate all of its protons to water to produce hydronium and chloride ion. Not all acids are that way, and so we're going to have to learn, first of all, to be able to identify what's a strong acid or a strong base, and then we're going to treat them differently when we're trying to determine or figure out or calculate how much of that proton has been donated. Now you'll notice here that we could drop a water molecule out of both sides. And so sometimes you will see this reaction written in this way, where hydrochloric acid breaks up to a proton plus chloride. Both of these are functionally equivalent because both are occurring in aqueous solution, in water. It's just that in this one, we've dropped the water out or crossed out of water on both sides of the reaction arrow. But both are functionally the same. Now, when we have an acid, all right, it's going to donate that proton to water to produce H3O plus an anion. Here the anion is nitrate because this is nitric acid. So the nitric acid donates its proton, and nitric acid is a strong acid, donates its proton to water to form H3O, and then the anion that's left over is nitrate because the acid that we're starting with is nitric acid. You can see that down here where we look at the actual chemical structures, and it's important, we talked about Lewis structures and we looked at organic molecules. Here we have the acid group. The acid group is a highly polar bond dealing with hydrogen. In this case, it's got an oxygen next to it. We normally would call this an oxo acid. Not all acids have to be that way. Not all have oxygen attached to that hydrogen. And you can see it's highly polar, with the oxygen being more electronegative and pulling those shared electrons toward it, to the point where that hydrogen almost falls off, like it's ready to go. It's ready to go somewhere else. And you'll notice over here the water. Here the water, we said the oxygen is partially negatively charged, while the hydrogen is partially positive due to the polarity of that molecule and the electronegativity of the oxygen. And I want you to notice that we said here we need a highly polar bond, and here we need a lone pair. All right, so the lone pair of this oxygen is going to reach out and it's going to take that hydrogen or take that proton away from the acid. All right, and so when we look for bases, normally we're going to look for things that have some lone pairs, because the lone pairs are going to be attractive to those protons that are being given off. And for an acid, we're going to look at something that has a highly polar bond that's involved hydrogen. Now, strong acids, we said before, strong acids donate all of their protons when dissolved in water. So notice the reaction arrow here. We've been talking about equilibrium all this time, but notice the reaction arrow points one direction. For strong acids, that arrow is always going to be a one-directional arrow. It's not in equilibrium. And this reaction is stoichiometric. All right, so if we say 1 mole of HA, all right, we start with 1 mole of HA, we would produce 1 mole of H3O as product. That's because this reaction goes to completion. It's not an equilibrium. And so we can do the same stoichiometric calculation that we've been doing since the beginning of our time in chemistry, which is taking 1 mole of HA to produce 1 mole of H3O. And if we start off with 1 mole of acid, we end up with 1 mole of H3O, 1 mole of hydronium ion. So it's a stoichiometric reaction, not an equilibrium. We're going to find that these are the simplest ones that we have to deal with, okay? Because we're going to get into next, how do we determine how much H plus is produced in a particular reaction, a particular acid-base reaction, and that's what we're going to get into in one of the next upcoming videos. Now, if we talk about a weak acid is an acid that doesn't donate all of its protons. It only donates a small fraction. And we've talked about these as well. You know, acetic acid is a weak acid. It will be maybe 5 or 10% ionized. And so, you know, these present a little bit more of a challenge because now it's not a stoichiometric reaction anymore. It's got the equilibrium error, the arrow pointing in both directions. So we have to worry about the equilibrium whenever we try to figure out, okay, how much H3O is produced whenever we start off with a certain amount of weak acid. All right? And so we look at this, it's an equilibrium. All those properties of equilibria are important for us here. Okay, so we're going to have to bring in all that stuff that we learned about equilibrium constants and equilibrium constant expressions. Now to show this, all right, here on the left-hand side, we might have a beaker that contains hydrochloric acid. Hydrochloric acid is a strong acid, or nitric acid like we saw before. Strong acids donate all the protons, lots of ions in solution, and so we get conduction back and forth. So this light bulb will light up very, very brightly. If the solution is less conductive, however, it's not going to conduct electricity in the same way, and the light bulb will not light up as much. Here we have a strong acid, here we have a weak acid. This might be hydrochloric acid, this might be acetic acid. And so the way we tell the difference between a strong acid and a weak acid is fairly simple. You may not like it, but it involves memorization. That's the only way around it. So we have to memorize or know what the 6 strong acids are. There's no way around it. We need to know hydrochloric and nitric and sulfuric and perchloric and hydrobromic and hydroiodic acid. We need to know those. We need to know what their formulas are, and we need to be able to recognize when we see them that that is a strong acid. All the other acids that you might run into are weak acids. Now, of course, it's an oversimplification. However, for anything that we do, and most of the things that I do as a chemist, that's going to be the case. If it's not a strong acid, it's going to be a weak acid. You won't have to know the list of weak acids. You just have to know if these ones are strong. If you have something else, it's got to be a weak acid. All right? So everything else, other than a strong acid, we'll consider to be a weak acid. All right, so now we're talking about bases. Bases accept protons. They take protons. We saw that already in the water and how the water molecule would accept that proton from nitric acid. Here we're going to talk about what's called a Bronsted base. Bronsted base is going to be a molecule that accepts a proton. So we have this base and we call the base X. You add that to water, it's going to take a proton away from that water, all right, and leave behind hydroxide ion. So before when we had an acid, we produced hydronium ion. When we have a base, we produce hydroxide ions. Now strong bases, just like strong acids, they will accept all protons that are available. All right, even if there's a weak acid around, it's going to take the proton. Strong acids want protons. And the simple thing, and we're going to see this again on a slide coming up, the simple thing about strong bases, they're all hydroxides. Hydroxide tends to be the strong base. And for us, anytime we see a hydroxide, we're going to think strong base. And here we have sodium hydroxide reacting with hydrochloric acid. All right, that hydroxide ion will steal that proton from that acid or accept that proton from that acid, that hydrochloric acid, to produce water. And then what's left over is the sodium ion and the chloride ion, which is sodium chloride. We know that in aqueous solution that sodium chloride wouldn't be like this. It would be sodium ions and chloride ions, but we're writing it in the full molecular type equation. All right. Now, if you want to subtract away all the spectators, so the sodium ions and the chloride ions, we'd be left with hydroxide ion plus proton, H plus, produces water. And that's a generic form for an acid-base reaction. And pretty much any acid-base reaction, if you get it down to its net ionic equation, it's going to look something like that. And so we just have to remember that if we have an acid that's donating a proton, there has to be a base that's going to accept it. And if we have a base accepting a proton, there's got to be an acid that's going to accept it. Okay, so now we're looking at acetic acid, all right, plus water to produce H3O. And acetate ion, we've seen this earlier. We saw this earlier in lab whenever we were dealing with the titration of vinegar, all right? And so we said vinegar with CH3COOH, weak acid. Why weak acid? Because it's not one of the 6 strong ones, okay? And what we want to try to understand from this particular slide is that there actually are like pairs of acids and bases here. So for instance, we know acetic acid is an acid, and we know the water here is acting as a base. But the funny thing about this is that whenever that water, that base, accepts a proton to become H3O plus, all right, it turns from a base into an acid. And whenever we have an acid that donates a proton, it goes from an acid to being a base. So we call these pairs of acids and bases that we see conjugate acids and bases. So here we have acetic acid, and then we have acetate, which is a base, now a base. We call that a conjugate acid-base pair. And here we have water, which is acting as a base, and here is hydronium ion, which is an acid. We call that a conjugate acid-base pair. And so we have 2 of those, and it's important that we can recognize conjugate acid-base pairs. And this all comes about because when a base accepts a proton, it becomes an acid. And when an acid donates a proton, it becomes a base. What's left over is now a base. All right? Now, it turns out that they're not equal. So we're starting off with something that's really weak, fairly weak acid. That means that the base probably is going to be a little bit stronger. All right? And we have something that's water's not a great base. All right? And it's going to turn into something that's a really good acid. And so we're going to see there's going to be that, what you call a leveling effect as we go through. And so we have the base and its conjugate acid, and then we've got this acid and its conjugate base. Now, how do we identify weak and strong bases? Well, strong bases are going to have hydroxide. Weak bases are bases that do not have hydroxide in them. Now you might say, how do I know these? Do I need to memorize them? And I'm going to tell you, no, that you don't. I generally will tell you, all right, if you have a weak base because they're a little bit harder to identify. But certainly you need to be able to identify those strong bases and know how to handle them when it's a strong base. And seeing, if I tell you that ammonia is a base, you need to be able to say, okay, it's not a hydroxide species, so it must be a weak base. Right? And weak bases, just like weak acid, where weak acid will donate only a portion of the protons that they have, weak bases will only take some of the protons available. So now we're back in a situation where it's in equilibrium. Here we have ammonia, it's a weak base. Here we have water, okay? It's going to steal some of those protons from water. Water will act as an acid, ammonia will act as a base, and then the ammonia will form ammonium ion, which is the conjugate acid of ammonia, and water, which is an acid, will form hydroxide ion, all right, acid, conjugate base, all right, except this doesn't happen stoichiometrically. It's not like 1 mole of ammonia produces 1 mole of ammonium ion, all right, it's in equilibrium, and again, all those properties of equilibria will hold true for weak bases, same as with weak acids. Strong acids and strong bases, they're different, and we're going to see that in a video coming up whenever we start calculating pH. All right, that's it for introduction to acids and bases. So, get started on the homework problems for these. Thanks.